Hi everybody, welcome to this video on the Fundamental Theorem of Calculus, Part 1. In this video, we're going to prove the first part of the Fundamental Theorem of Calculus. We're going to introduce a new rule, the additivity rule for definite integrals. This rule will be used to prove the theorem. We'll start by stating the theorem. If f is a continuous function on the closed interval from a to b, then the function capital F of x, which we can express as the integral from a to x of f of t dt, has a derivative at every point x in the closed interval from a to b, and its value d capital F dx, which is equal to the derivative with respect to x of the integral from a to x of f of t dt, that's equal to f of x. This theorem is what we're going to prove in this video. We first introduce a new rule, the additivity rule for definite integrals. This rule is shown here at the top of the screen. And we're going to explain this rule using this plot shown at the bottom of the screen. So here we got the plot of a function y equals f of x, with that function plot highlighted in blue. We can calculate the shaded in green net area between the function curve and the horizontal axis from the point A to the point B as being equal to the integral from a to b of f of x dx. And that integral from a to b of f of x dx, that's been written there inside the shaded in green region. We can calculate the shaded in yellow net area between the function curve and the horizontal axis from b to c as being equal to the integral from b to c of f of x dx. And that integral from b to c of f of x dx, that's been written there inside that shaded in yellow region. Our additivity rule for definite integrals is saying that the integral from a to b of f of x dx, which gives us that net area for the shaded green region, plus the integral from b to c of f of x dx, which gives us the net area for that yellow shaded region, that's equal to the integral from a to c of f of x dx, which is the net area for that entire complete shaded region shown in that plot there. Now, what we can do is, with that equation at the top of the screen, we can rearrange that. We can move the integral from a to b of f of x dx to the right hand side of the equal sign. And when we do that, we can express the integral from b to c of f of x dx, which is equal to the net area for the yellow shaded region. We can express that as being equal to the integral from a to c of f of x dx, which gives us the net area for that entire complete shaded region, minus the integral from a to b of f of x dx, which gives us the net area for that green shaded region. We're going to use this rule in this form in our proof of the theorem. This rule, it is inherited from a rule which holds for Riemann sums. If you'd like to learn more about Riemann sums, please click on my video link shown here on the screen. For now, we continue with the proof. So first of all, we're going to state again what we're about to prove. If f is a continuous function on the closed interval from a to b, then the function capital F of x can be expressed as the integral from a to x of f of t dt, and that has a derivative at every point x in the closed interval from a to b, and its value d capital F dx, which is equal to the derivative with respect to x of the integral from a to x of f of t dt, that's equal to f of x. So we're going to prove this now. We start with the difference quotient of the function capital F of x. This is shown here as capital F of x plus h minus capital F of x divided by h. This difference quotient of capital F of x, this is equal to the rate of change of the function capital F of x over the interval with length equal to h. From our definition of the derivative of our function capital F of x, we express as d capital F dx, and that it's equal to the limit as h approaches 0 of our difference quotient, capital F of x plus h minus capital F of x divided by h. We prove the theorem by showing that this limit as h approaches 0 is equal to f of x. We next express capital F of x and capital F of x plus h in terms of their defining integrals. We express capital F of x as being equal to the integral from a to x of f of t dt. And we express capital F of x plus h as being equal to the integral from a to x plus h of f of t dt. If you'd like to learn more about expressing capital F of x in terms of a definite integral, please click and view on my video, which is linked here at the top of the screen. For now, we will continue with the proof. When we substitute these values into the numerator of our difference quotient, which is the top part of the fraction of our difference quotient, we get the following: that capital F of x plus h minus capital F of x, that's equal to the integral from a to x plus h of f of t dt, minus the integral from a to x of f of t dt. So what we've done here is we've replaced capital F of x plus h with the integral from the top right hand of the screen, and we've replaced capital F of x with the integral from the top left hand side of the screen. So we have the numerator of our difference quotient expressed as the difference of these two integrals. We now use the additivity rule for definite integrals. This is the rule which we described and explained earlier in this video using this plot here on the right hand side of the screen. When we apply this rule to the equation at the top of the screen, we can rewrite the numerator of our difference quotient to be capital F of x plus h minus capital F of x is equal to the integral from x to x plus h of f of t dt. So looking at our rule at the middle of the screen and the equation that we started with at the top of the screen, what we're doing is that instead of working with f of x dx, we're just working with f of t dt. And instead of working with a definite integral from a to c minus a definite integral from a to b, in our case we're working with a definite integral from a to x plus h minus a definite integral from a to x. When we substitute those values in, we get that the numerator of our difference quotient, it's equal to the integral from x to x plus h of f of t dt. So we have the numerator of our difference quotient expressed as the following equation at the top of the screen. we can now rearrange and express the difference quotient as being equal to 1 over h times that numerator, capital F of x plus h minus capital F of x. And when we substitute in for the numerator of our difference quotient that integral from x to x plus h of f of t dt, we get that our difference quotient is equal to 1 over h times the integral from x to x plus h of f of t dt. So we have our difference quotient expressed as 1 over h times the integral from x to x plus h of f of t dt. Now we can calculate the mean value of a function f over a closed interval from a to b as being equal to 1 over b minus a times the integral from a to b of f of x dx. When we look at that equation at the top of the screen, and when we look at the terms on the right hand side of the equal sign, if we wanted to calculate the mean value of that function f of t over the closed interval from x to x plus h, we could do that using this equation for the mean value of a function shown here in the middle of the screen. We're going to do that now, and we're going to do that on the next line. The mean of our function f of t over the interval from x to x plus h, well, that will be equal to 1 over x plus h minus x times the integral from x to x plus h of f of t dt. And when we simplify that fraction, we get that the mean of our function f of t from x to x plus h, that's equal to 1 over h times the integral from x to x plus h of f of t dt. If we look at the terms inside both of those red rectangles, the terms inside those red rectangles, they are the same, they are equal. So what we're actually saying here with that equation at the top of the screen is that we're saying that the difference quotient of our function capital F of x over that interval of length h, we're saying that that's equal to the mean value of the function f of t over that interval from x to x plus h. We now use the mean value theorem for definite intervals. This theorem states that for a continuous function on a closed interval from a to b, the value of that function at some point on that interval will be equal to the mean value of the function over that entire closed interval from a to b. This term highlighted here in the red rectangle, f of c, this is the value of our function f at some point in that closed interval from a to b. And the value of the terms inside this red rectangle, this is the average, the mean value of the function f over a closed interval from a to b. According to this theorem, the value of looking at that equation at the top in the red rectangle, according to this theorem, the value of the set of terms on the right of the equal sign inside that red rectangle, that is equal to one of the values of our function f in the interval from x to x plus h. And we refer to that value of the function f as f of c, highlighted here in that red rectangle. This means that when we evaluate our difference quotient of capital F of x on some interval h, it will be equal to a value of our function f on this interval. we describe that function value as f of c, where x equals c. So what we want to prove is that the derivative of our function capital F of x, which we express as d capital F dx, and which we can express as the limit as h approaches 0 of our difference quotient, capital F of x plus h minus capital F of x over h, we want to prove that that is equal to f of x. Because we've been able to express that the difference quotient, capital F of x plus h minus capital F of x over h, because we've been able to express that difference quotient of capital F of x on that interval of length h, that's equal to some value of the function f on that interval from x to x plus h, we can work out what happens to the difference quotient as h approaches 0 by observing what happens to f of c as h approaches 0. So if we look at this plot here at the top of the screen, here we've got a plot of our closed interval from x to x plus h, and we've got the point c on that closed interval. As h approaches 0, the endpoint x plus h approaches x. And as x plus h approaches x, the value c approaches x. So as h approaches 0, x plus h approaches x. And as x plus h approaches x, the value c approaches x. And as c approaches x, f of c approaches f of x. In other words, the limit as h approaches 0 of f of c is equal to f of x. From the start, we have the derivative of our function capital F of x, which we express as d capital F dx, that's equal to the limit as h approaches 0 of our difference quotient, capital F of x plus h minus capital F of x divided by h. That's from our definition of the derivative. Now, we can express that as being equal to the limit as h approaches 0 of 1 over h times the integral from x to x plus h of f of t dt. Now, we can do this by expressing the function capital F in terms of its defining integral, and by using the additivity rule for definite integrals. We can express this as being equal to the limit as h approaches 0 of f of c by using the mean value theorem for definite integrals. And as h approaches 0, x plus h approaches x. And as x plus h approaches x, then the value c approaches x. And as the value c approaches x, then f of c approaches f of x. So our limit as h approaches 0 of f of c, that's equal to f of x. And this concludes the proof. So this is what we've just proved, the Fundamental Theorem of Calculus Part 1. If f is a continuous function on the closed interval from a to b, then the function capital F of x, which we can express as the integral from a to x of f of t dt, has a derivative at every point x in the closed interval from a to b, and its value, d capital F dx, which is equal to the derivative with respect to x of the integral from a to x of f of t dt, that's equal to f of x. So to summarize, in this video we have proved the first part of the Fundamental Theorem of Calculus. If you found this video useful, please subscribe to the channel to receive more content. Thank you very much for your time, and see you next video.